Next up on our list of things that we need to learn, or at least remember from last year as we journey towards calculus, are identifying and be able to deal with inverse functions. So the way that we've talked about inverse functions before, we use this notation of f inverse. So don't read that as f to the negative first power, or the inverse function is the function that reverses the effect of f of x. So for example, the inverse of f of x is equal to x cubed is the cube root. And the inverse of 7x is 1 or x over 7. Inverses undo the applied operation. And we kind of intrinsically know that. So if we were building our function x cubed, or we say f of x is equal to x cubed, our x's are inputs. So if we use -2, -1, 0, 1, and 2, we would get the powers of our values back out. But for its inverse, we are switching the x and y. We're switching the inputs and the outputs, or domain is swapped with the range, provided that it meets certain conditions. So all of the outputs that we just wrote down will be our inputs. So the cube root of -8 is -2, or the cube root of -1 is -1. 0, the cube root of 1 is 1, and the cube root of 8 is 2. You can see how the x and y values are just swapped. So the steps for finding an inverse is step 1, swap the x and y. Wherever you see an x, you're going to write y. Wherever you see a y, you write x. And step 2, solve the equation for y. If an inverse exists, it is unique. But the trick about inverses is that not every function has an inverse. So we just looked at x cubed. The inverse of that is the cube root of x. What happens if we look at x squared? If we did the exact same thing with our function x squared, plugging in the same values, -2, -1, 0, 1, and 2, we would see that we get 4, 1, 0, 1, and 4. So if x squared is invertible, then its inverse would just simply be switching the y value and the x value. But there's a problem when I do this. Make sure I write these numbers right. 4, 2. If we graphed this table, we would have a sideways parabola. And since you guys all know, that does not pass the vertical line test. Pass VLT. So it is not a function. If it's not a function, then we don't deal with it. So the inverse function isn't a function. So when does a function have an inverse? The graphical way is saying it passes the horizontal line test. But the mathematical way of telling if something is invertible is if every input goes to exactly one output, where we call that 1, 2, 1. I'm just going to write down what I have in my notes. We will say if f of x fails the HLT, horizontal line test, f inverse will fail the vertical line test. So that's how you tell if something is invertible or not. It's a key skill because when we talk about derivatives, we'll need to understand this idea of inverses. And then when we're talking about inverse trig, this is the same concept. So show that f of x is equal to this equation is invertible, and then determine the domain and the range. So first, if we look at our function, we're looking for the domain of f. So I'll write d sub f. We look at the denominator, and we say, what makes this denominator 0? So we say x can't be 1/5. So I'm just going to take that value that I just wrote and say that is my domain. Likewise, we would say our range is limited by the coefficients. We look at the degree of the top, it's 1. The degree of the bottom is 1. So we do coefficient divided by coefficient. We say the range is y cannot equal 3/5. That's my horizontal asymptote. This would be my vertical asymptote. So that's the domain and range of our function initially. I'll just make that a little bit smaller. I can delete that red. If we are going to find the inverse, step 1, wherever we see a y, we write x. Wherever we see an x, we write y. 5y minus 1. Next, we're going to solve for y. So the first thing we're going to do is we're going to cross multiply, because this is a cross and equal sign. And then I will distribute the x equals 3y plus 2. This second step is the one that most people make a mistake on. We want to get the y's on the same side, and we want to get everything else on the other side. So get all y terms on the same side. Now, if we're looking at these two terms, I'm just going to put this over here. If we factor out the GCF, which is y, we're left with 5x minus 3 is equal to x plus 2. That means our inverse function is x plus 2 over 5x minus 3. Or we could call that f inverse. X plus 2 over 5x minus 3. Which means our domain of our inverse function, we look at the denominator and we'll say x is not equal to 3 over 5. And our range of our inverse function is going to be y is not equal to 1/5. Note, you don't even have to be able to invert these to know that the domain of the function is the range of the inverse. The range of our function will be our domain of our inverse function. If we're thinking about a function graphically in comparison to its inverse, let's say we're looking at the graph f of x is equal to 2 to the x. Well, if we are graphing that exponential function, 2 to the 0th power is 1, 2 to the 1st power is 2, and then 1/2, our function will look like this exponential curve. And we could be a point anywhere along this and call that a comma b. What the inverse function is, graphically, is the reflection over the line y equals x. So when we are switching our x value with our y value, a comma b becomes b comma a. This value of 0, 1 becomes 1, 0. This value of -1, 2, or negative 1/2 becomes 1/2, -1. And so we get this inverse function, which is the reflection over the line, reflection over y equals x, and we get our inverse function of our log base 2 of x. That is the visual that we're doing when we're switching the x value with the y value, which then allows us to talk about our inverse trig functions, which I told you are a little bit different. So if we're dealing with inverse sine, note that inverse sine, we are switching our sine function from -π/2 to +π/2, because otherwise our function would not pass the horizontal line test. So we are going to say that the domain of our inverse function is from -π/2 to +π/2. We'll talk more about this in class, but on your unit circle, that's saying the right side of the circle. For inverse cosine, let's put an x there. Our domain is from 0 to pi. We use brackets, meaning we can be those values. And just as a visual, inverse cosine, we just look at the upper portion of the unit circle. Inverse tangent, the domain is from negative pi over 2 to positive pi over 2. For inverse cosecant, which is the reciprocal of inverse sine, it's negative pi over 2 to 0, union, parentheses, 0, comma, pi over 2, bracket. For inverse secant, it is 0 to pi over 2, parentheses, union, parentheses, pi over 2 to pi, bracket. Now notice, if these are reciprocal functions, and we're looking at 0 or pi over 2, if I plug pi over 2 into cosine, you get 0. And 1 over 0 is undefined. That's why we're not including it. And last inverse trig function that we would need to know about its domain would be from 0 to pi, which is inverse cotangent. So again, we need to do a little practice with those. But what happens when we then start applying trig functions and inverse trig functions at the same time? Well, we call these triangle problems. Remember, anything that we plug into a trig function is really an angle. We plug in angles and we get values out. So the way I want you to approach these problems, let's see if I can draw a triangle and it matches, is by making a picture, marking off our angle, and we're using this inside part is we're saying our angle is equal to the inverse tangent of x. Well, if we took the tangent of both sides, this is just the inside piece. I'm looking at the inside first. If I took the tangent of both sides, I'd be left with tangent is equal to x over 1. Tangent is the opposite over the adjacent side if we're looking at TOA in SOHCAHTOA. So that would be x, and then the adjacent side would be 1. If we did the Pythagorean theorem, we would have x squared plus 1 squared is equal to c squared. So this c is equal to x squared plus 1. That's just doing some algebra to fill this out. The question then becomes, what is the cosine of our angle? So if we're looking at cosine, cosine is adjacent and hypotenuse. So our cosine value of our angle is equal to the adjacent side over the hypotenuse. And as you guys all remember, we don't leave square roots on the bottom, so we would rationalize this. This would be the square root of x squared plus 1 over x squared plus 1. So same thing. We're asking for the cosine of this value. Whatever goes inside a trig function is our angle. So all we have to do is draw a right triangle, mark off our base angle. We're saying that inverse cotangent of 1 is equal to our angle, or the cotangent of our angle is 1. Cotangent is adjacent over hypotenuse, adjacent over opposite. So that means 1 squared plus 1 squared is equal to our hypotenuse, which is 2. So our hypotenuse would be root 2. And I'm asking you, what is the cosine of this angle? Well, it would be adjacent over hypotenuse, 1 over the square root of 2, which should look familiar because that's a 45, 45, 90 triangle. And we're left with the square root of 2 over 2. We're going to do one more, and then this will be the end of this video, is compute tangent of inverse secant of -2. This is where it's important to know where this is located. Because going up, down, left, or right, if it's negative, we have to think cosine and inverse secant only exist in the first and second quadrant. So I draw my picture in the second quadrant. Secant is the same thing as, so this is inverse secant of -2 is equal to our angle, or -2 is equal to secant of our angle, which is another way of saying -1/2 is equal to the cosine of our angle. We just took the reciprocal of both sides. Well, this is adjacent over hypotenuse. The adjacent side is negative. The hypotenuse is always going to be positive here. And so to find the missing side, we'd have the square root of 3. Now, if I ask you what is the tangent in that triangle, we would do opposite over adjacent, square root of 3 over -1, which is the negative square root of 3. Once we're able to know these basic properties, it's pretty simple to find the values. If we're doing a look ahead, we're going to talk briefly about solving equations for specific variables. You've probably done that in many of your science classes. We're going to reintroduce this concept of simplifying the difference quotient. We have some geometric shapes that we should probably be familiar with. And otherwise, that takes us, oh, and the last piece, everyone's favorite, are piecewise functions. So we have about two more videos left for us to cover, and then we will be testing on our review chapter. So see you in the next one, Falcons.